Okay, welcome to part 2 of the B-field lab. Okay, so in this part we're going to calibrate our pickup coil or our magnetic field probe, okay, and come up with a conversion factor to convert the peak voltage to a magnetic field. Okay, so here again is our apparatus. I have a signal coming out of the function generator, going into the short solenoid, comes out of the short solenoid and through this resistor, and then back to the function generator. Then I have channel 1 of the oscilloscope measuring the voltage across the resistor, okay. And then I have channel 2 of the oscilloscope connected to the pickup probe, okay, or the pickup coil here, okay, which is our magnetic field probe. So essentially there's a magnetic field being generated by the solenoid, and the flux from that magnetic field is passing through this pickup coil, which is giving me a voltage right here, and I'm picking that voltage up on my oscilloscope. So channel 1 is the voltage on the resistor, okay, and channel 2 is the voltage. Channel 2 is the voltage on the pickup coil. So I can display both of them at the same time there. The bottom one is the voltage on the resistor, and the top one is the voltage on the pickup coil. So we use the voltage on the resistor going into the long solenoid to measure the current, okay. So I did that, and we measured that voltage to be 5 volts peak. The resistor is 100 ohms, so therefore the peak current going through the long solenoid is 50 milliamps, okay. So we can plug that into this formula right here, okay. This formula, where is it? This one. So we can plug that into this formula right here, okay. This is the magnetic field at the center of a short solenoid, okay. Mu0 times the number of coils times the peak current. In this case, R is the radius. Don't forget, R is the radius of the coil, of the solenoid. So let me write that down, okay. R is the radius of the solenoid, okay. So R is the radius of the solenoid, okay, which I've measured. So the radius of the solenoid was 10.8 centimeters, okay. So the radius, the diameter of the solenoid was measured across here, which is 10.8 centimeters. So the radius is going to be half of that, okay. So the radius of the solenoid would be 5.4 centimeters, okay. So I'll just write that down right here, 5.4 centimeters, okay. So the radius of the solenoid is 5.4 centimeters. And the current we measured was 50 milliamps, okay. I was 50 milliamps, okay, so I'm going to write that down there. So now you can calculate the magnetic field at the center, and the number of coils, the turns, was 28. So I just basically counted the number of wires right here, 1, 2, 3, 4, 5, all the way up to 28. So there are 28 current loops here. So you notice here that this solenoid does have a finite thickness. So later on in the analysis, we'll actually calculate the exact magnetic field for that finite length, okay, which is 4.4 centimeters, and compare it to our approximation, assuming that all the coils are at the same in the same plane. Okay, so this formula that we used right here for this formula assumes that all the coils are in the same plane. Okay, so we will compare our magnetic field for the finite one later in the analysis. Okay, so now we have a method to calculate the magnetic field due to our the voltage on this pickup coil. So we can convert the voltage on the pickup coil to magnetic field by measuring the voltage of the magnetic field right at the center of this coil. Okay, so we can take our pickup coil now and essentially measure the voltage. I'm going to zero my voltmeter here. Sorry for the blackout, but here we go. Okay, so I'm holding the pickup coil right on the axes of the solenoid, right in the center. Okay, right in the center here, and I can measure the voltage on the oscilloscope. Here is the voltage being induced by the pickup coil. Notice that if I rotate my solenoid to 90 degrees, okay, that the voltage essentially disappears, okay, because there's no flux going through it, okay. There's essentially no flux passing through our solenoid like that. The magnetic field points along the axes of the solenoid. So we're going to make sure we get maximum flux by pointing our solenoid along the axes here. Okay, so I'm just going to adjust that so that the voltage is maximized, okay, and get it right in the center. And I can measure that voltage, and that voltage turns out to be 2,800 milliamps, okay? So 2,800 milliamps is the peak voltage at the center. So the pickup coil peak voltage is 2,800 millivolts at the center of the solenoid. Okay, so there we are. The pickup coil peak voltage is 2,800 millivolts at the center of the solenoid. So now I can calculate a conversion factor. Okay, a conversion factor is going to convert peak voltage to magnetic field, okay, by multiplying the voltage by a conversion factor. Okay, so alpha is going to be the PUC. It's going to be the magnetic field at the center that we calculated, okay, using our formula, where BP is just going to be mu zero IP times N over 2R, right? Okay, so that's going to be our BP that goes in here, and this is the PUC VP, okay, that goes in here. So our conversion factor, you can find a conversion factor now to convert the peak voltage measured by the PUC to a magnetic field. Okay, so essentially you just multiply that voltage by magnetic field to get it. So essentially, when you get your data, okay, when I give you this data sheet here, you'll essentially multiply this peak voltage in millivolts to by the conversion factor to get the magnetic field in Tesla. Okay. Okay. So basically, you'll get another column on your spreadsheet here, BP, which will be equal to alpha times VT, and this will be in Tesla. Okay. Okay. So you basically will convert all these voltages to Tesla by multiplying them by the conversion factor alpha. Okay. Okay. So, so that ends the calibration phase. So I'm going to stop this video, and then we're going to look at the actual lab measurement. Okay, next.